Hey guys, here are notes for 9.3 section. It's chords and arcs. And first we want to talk about a central angle. Now if you see an angle that has a vertex that's the center of the circle, then you have what you call a central angle. The two sides of the angle are both radii. PA is a radius and PB is a radius, and therefore it makes a central angle. Now central angles equal their arcs. So if this, let's say this looks like about a 90-degree angle. So if this is 90-degree angle, then this is a 90-degree arc right here. There's 360 degrees in one whole circle, so this would be 90 of those degrees right here because it's a 90-degree angle. So central angles and their arcs are equal. We'll do an example down here, but let's get a few vocab terms in real quick. Minor arc is an arc that's less than 180. A major arc is an arc that's more than 180, and you must use 3 letters for a major arc. So a minor arc would just be this AB right here that's less than 180 degrees, would be a whole line here, so it would be half a circle. So a minor arc is less than half a circle. A major arc is more than half a circle, and you must use 3 letters. So if I wanted to do this backwards arc right here, I couldn't say AB because I'd be doing the shorter way. I would have to say ACB to show that I'm going backwards, ACB. And then a semicircle is an arc where the endpoints are on the diameter of the circle, meaning it equals 180 degrees. Now you can use 1, 2, or 3 letters for a semicircle, but it's going to be exactly half of a circle. So half a circle would be a semicircle. Now example 1, what is the measure of arc AB? Well, if the central angle is 60, then the arc is also 60 degrees. So this arc right here is a 60-degree arc because its angle is 60 degrees. What is the measure of arc BC? Well, B to C is a diameter, so if the endpoints are on a diameter, it has to be 180 degrees. That is exactly half a circle. We would call that a semicircle. And then what is the measure of ACD, which means we got to add this angle plus this angle. Well, if this is 60 and this is a linear pair right here, this has to be 120. They have to add up to 180 degrees. So if this is 120 right in here, then 120 plus your 110, get 120 plus 110, so this angle is going to be 230 degrees. You can see this arc right here is going to be a 230 degree arc because this angle was 230 degree angle. Angles that are in the center are equal to their arcs. And again, you can pause it anytime you need to. Okay, find the measure of each arc. So another example here, if GE adds a 40 degree angle plus an 80 degree angle, that means the arc GE is going to be exactly 120 degrees. GEF is more than 180. It's 3 letters. It's a major arc passing through E over to F. 40 plus 80 plus 110 is actually going to be 230 degrees. 120 plus 110, 230. GF, you'd have to go the shortest way from G to F. So from G to F, the shortest way is right here. So they want to know what this arc that's missing would be, and if these 3 add up to 230 and all 4 of them have to add up to 360, then GF has to be 130 because 230 plus 130 is going to give you 360. Let's see the next one over here. It says what can we say about arcs AB and arcs BC if we know their chords are congruent? That's what those lines mean, they're congruent. So we know that AB chord is congruent to BC chord. That means that arc AB has to be equal to arc BC because they're both cutting off the same amount of the circle. So use the phrase if and only if, you'd want to put something like this. 2 arcs are congruent if and only if their chords are congruent. So if 2 chords are congruent, then 2 arcs have to also be congruent. That's another way to say it. 2 congruent chords means you've got 2 congruent arcs. Now let's think about a radius with a chord or a diameter with a chord. Either way works. The perpendicular bisector, that means it's 90-degree angle and it's bisecting, of any chord must contain the center of the circle. That means it's either going to be a radius or it's going to be a diameter. But if you've got a chord and you've got another line that is perpendicular to it and it cuts it in half, then you have to be in the center of the circle. You have to either be a radius or a diameter, one of the two. Anytime a radius or diameter bisects a chord, it must be perpendicular to that chord. If it's cutting this chord in half, the only way it could have done that was to be a 90-degree angle. That's what this last one's saying. Again, you can pause it whenever you need. Okay, let's talk about making a circle chart. A circle chart or a pie chart breaks a circle up into percentages. And for us, we're going to need to take that percentage and turn it into a degree angle so that we have the degree arc as well. So we're going to start with percent, and we're going to also figure out the degrees that goes with this percent. So we've got 500 students, and 75 of those students are freshmen. So the percent, 75 out of 500, was going to be 15% of my school here, the class or whatever, is freshmen. So if we want to find out what 15% would be, we would take 15% times it by 360, and that would tell us that it's going to be a 54-degree angle. 15% of 360 would be 54 degrees, because the 360 is in degrees. 100 sophomores would be 20%, and 72 degrees. And I'll go through these quick because you've already seen how the first one works, and they all work the same. 145 juniors, which is 29%. And it would be about 104.4 degrees when you times it by 360. 180 seniors, 36%, so it's 129.6. If you added up all these percentages, you get 100% because you've got a whole circle. If you add up all these degrees, you get 360 degrees, again, because you have a whole circle. So what we want to do then is we want to make our degrees correct, so we would have to start with a straight line here. And first thing we do is we would measure 54 degrees and put freshmen in there. We'd color it a certain color. We would measure 72 degrees and put sophomores in there. We would measure 104 degrees, approximately, give or take. We just rounded it off. 104 degrees, and you get juniors. And then you do round it off to 130 degrees, and you get your seniors. So that would be your circle chart. You color code it, whatever you need on a circle chart. But you got to correlate the percentages with the degrees if you want your circle chart to be accurate. Example 4, this is your new logo. You've got this triangle inside of the circle, and you want to know what the radius from like O to A, or O to C, or O to B, what would the radius of our logo be if these are all the dimensions of it? Well, what we need to do is use the Pythagorean theorem, because of the right triangle that you see right here. You see this right triangle? We could use Pythagorean theorem, and we know two sides of that right triangle. We know radical 80 and we know 4, so we could actually solve for DE just by doing Pythagorean theorem. So let's do that. DC squared, that's our hypotenuse squared, equals DE squared plus EC squared. That's just setting up the formula for us. The next step is to plug in the numbers. DC is radical 80. DE we don't know yet. From D to E we don't know that piece. Look at it, follow along so you can see it. There's DE. We don't know the biggest leg of our right triangle. We do know EC is 4. That's down here at the bottom. We know this little piece is 2. That doesn't come into play yet. So we're going to square radical 80, and you're going to get 80 because the square root and the square will cancel out. This is going to come down. 4 squared is 16. You're going to subtract 16 on both sides. You're going to square root both sides. You're going to get DE is 8. So from D to E is 8, plus you've got 2 more here for the whole diameter. So that means that this piece DE plus this piece EB is equaling your diameter. So 8 was DE and EB is 2. That's a 10 diameter. So that means the radius has to be half of our diameter. Take 10 divided by 2, you get 5, and that's your radius of the circle. All right, moving on. Let's talk about arc length. Arc length is the measure of part of the circumference. The whole circumference would be the amount around the circle. the length of an arc would just be how long is it from A to C. If I use scissors and cut this off here and then cut it off here and I laid it straight and I measured it, how much would it be? That's what arc length is. To find arc length, you multiply the percent that you want by the circumference. Let's say this is representing 100% of the circumference, but I only want 20% of it. So you'd multiply 20% times the whole circumference and you would get that piece. So that's kind of what the formula is. To find the part that we want, we find out how many degrees it is out of 360 because the whole thing is 360. So find the degrees over 360 and you can multiply that by the whole circumference, which we know is 2 pi r from our formula, area formula, or circumference formulas. So let's apply this formula right here to this problem. It says find the length of arc AC. So the arc length, this AC is the part that we want, the part times the circumference. So it's going to be the part that we want. We want 60 degrees out of the whole 360 times the circumference, which is 2 times pi times radius of 6. My radius is 6. So it's the part that we want times the whole circumference. The part that we want can be reduced to 1/6 and then times that by 12 pi. You could actually cross cancel here. 6 goes into 12 2 times. So really you're just going to end up with 2 pi. And if you multiply 2 times 3.14, you're going to get 6.28 as your arc length. So from A to C, if I cut it off, I'd be having a length that would be 6.28 centimeters. That's called arc length. And one last slide for notes is going to be called area of a sector. Now, similar to arc length, the length of an arc is part of the circumference. In this case, the area of the sector is just part of the area. Not the whole area, not what fills in the whole circle, just what fills in part of the circle. So area of a sector is the measure of part of the area of the circle. Just part of the circle, not the whole circle, just part of the circle. To find the area of a sector, you just multiply the percent that you want by the area of the sector. It's the exact same formula. You'll see the exact same formula. The central angle over the 360 is the percent that we want. And then this time I got to use the area formula, not the circumference formula. Pi r squared is our area formula. So if I want to find the area of this shaded part, I need to use my formula, and I need to plug in my central angle, 75 out of 360. The whole angle all the way around would be 360, but I only want 75 degrees of that 360. So if I take 75 and divide it by 360, I get 0.208. And then times pi r squared times pi times 8 squared, which would be 64 pi. Multiply all this on my calculator, I get approximately 41.9 square centimeters for this shaded area right here, the shaded part. And those are notes for 9.3. Don't forget your practice problems. There is one page there. There's one page there. They're on your notes. So we'll see you guys later.